welcome back to educator.com. Today we're going to talk about roots, also called zeros, of polynomials. We briefly went over what a root is when we talked about the properties of functions, but let's remind ourselves, the zeros of a function, the roots of an equation, and the x-intercepts of a graph are all the same thing. They're inputs, which is just x values, where the output is 0. It's where it comes out to be 0, things that will make our expression spit out 0. The roots, zeros, x-intercepts of f of x equals x squared minus 1 and y equals x squared minus 1 are x equals negative 1 and x equals positive 1, because at those two values, f of x and y are equal to 0, right? If we plug in negative 1 squared will become positive 1, and then minus 1, 0. We plug in positive 1 squared, 1 minus 1, 0. Those two things cause it to spit out 0, so the roots of the polynomial are the x values where the polynomial equals 0. The roots of the polynomial x squared minus 1 are negative 1 and positive 1. Being able to find roots in functions is important for many reasons, and it will come up very often when you're working with polynomials. If you continue on to calculus, you'll see how roots can be useful for finding lots of information about a function, so they're very important to have a grasp of what's going on there and be able to find roots. Roots in graphs. If you have access to the graph of a function equation, it's very easy to see where the roots are. Of course, you might not see precisely because it is a graph after all, and it might be off by a little bit, but you can get a very good sense of where they are. It's where the graph cuts the horizontal axis, the x-intercepts. Why? Because here we've got f of x equals 0 or y equals 0, depending on if it's a function or an equation. Since that means our height is at 0 there, then every place where we cross the x-axis must be a root. Simple as that. This also gives us a nice mnemonic to remember what the word root means. It can be a little hard to remember the word root since we aren't that used to using it, but we can remember it as where the equation or the function grows out of the x-axis, right? Where it's 0. It's like it's the ground. Think of it as a plant rooted in the ground. A function or equation has its roots in the x-axis, right? A tree has its roots in the earth, and a function has its roots in 0, in a height of 0. So a root is where it is growing up and down, right? So it is where it is held in our plane, held in our axes, and that's one way to remember what a root is. How do we find the roots of a polynomial? Well, at first we might try a naive approach and attempt to solve the way we're used to. Naive is just what you've done before, what seems to make sense without ever really having had a whole lot of experience about it. So the naive attempt would be probably to just isolate the variable on one side. That's what we did with a bunch of other equations before, so let's do it again. Now, in some cases, this will actually work and we'll find all the real solutions. For example, if we've got f of x equals x minus 3, then we set it equal to 0 because we're looking for the roots. We're looking for when 0 equals x minus 3. We move that over and we get x equals 3. Great. Or if we had y equals x cubed plus 1, we set that to 0, and we have 0 equals x cubed plus 1, because we're looking for what x's causes us to have 0 equals x cubed plus 1. So we've got x cubed equals negative 1, we take the cube root of both sides, and we get x equals cube root of negative 1, which is also just negative 1. So in both of these cases, the naive method of isolating for variables worked just fine, but that's definitely not going to be the case for all situations. The naive method of isolation will fail us quite quickly, even when used on simple quadratic polynomials. Consider f of x equals x squared minus x minus 2. Not a very difficult one, but this method of trying to isolate will just fail us utterly if we use it here. So 0 equals x squared minus x minus 2, we might go, well, let's get the numbers off on one side. So we've got 2 equals x squared minus x, right? But then we're like, well, we don't have just x, so let's pull out an x, and we get 2 equals x times x minus 1, and well, we're not really sure what to do now, so let's try another way. 0 equals x squared minus x minus 2. Let's move x over, because we're used to trying to get just x alone. So we've got x here, but then we've also got x squared here. So let's divide by x. We get 1 equals x minus 2 over x. Once again, not really sure what to do. Let's try again. 0 equals x squared minus x minus 2. So let's move over everything but the x squared. Maybe x squared is the problem. So we'll get x plus 2 equals x squared. We take the square root of both sides. We remember to put in our plus minus signs. Plus minus square root of x plus 2 equals x. I don't really know how to figure out what x's go in there to make that true. So in all three of these cases, it's really hard to figure out what's going on next, right? Yuck. If we're going to try to isolate, we're going to get these really weird things. This method of isolation that we're used to isn't going to work here because we can't get x alone. We can't get the variable alone on one side. It's not going to let us find the roots of polynomials if we try to isolate. But at least we could trust it in those previous examples. We saw we can trust it when it does work, right? So we might as well try it first. Nope. Even worse, the naive method of isolation can make us miss answers entirely, even though we think we will know them all. So we'll think we found the answers, but in reality we'll only have found part of the answers. Consider these two ones. If we've got 0 equals x squared minus 1, we move the 1 over, and then we take the square root of both sides. Square root of 1 is 1, square root of x squared is x. Great. For this one over here, we've got 0 equals p squared plus 3p, so we realize, oh hey, we can divide both sides by p, and since 0 over p is just 0, we've got 0 equals p squared over p becomes p, 3p over p becomes 3, so we've got 0 equals p plus 3, we move the 3 over, we got p equals negative 3. Great, right? We found the answers. Not quite. Those above things are solutions, but in each case we've missed something. We've been tricked into missing answers by trying to follow this naive method. The other solutions for this would be x equals negative 1 and p equals 0, respectively. The mistakes that we forgot were a plus minus symbol over on this one. We forgot to put a plus minus in when we took the square root, and then if the other one was dividing by 0, because when we divided, we inherently forgot about what about the possibility that if we were actually dividing by 0, we couldn't divide by 0. So those were the two mistakes. But even if you personally wouldn't have made those same mistakes, this example shows how it's easy to forget those things in the heat of actually trying to do the math. You might forget about that, and you might accidentally make one of these mistakes, so it's risky to try this method of isolation. We need something that works better. We find the roots of a polynomial by factoring it. We break it into its multiplicative factors. Let's look at how this works on the example that we couldn't solve with naive isolation. We've got f of x equals x squared minus x minus 2. So we have 0 equals x squared minus x minus 2, because we're looking for when is f of x equal to 0. And then we say, let's factor it. Let's break it into two things. So we have x minus 2 and x plus 1. And if we check, that does become it, right? X times x becomes x squared. X times 1 becomes plus x. Minus 2 times x becomes minus 2x. Minus 2 times 1 becomes minus 2. So yes, that checks out to be the same thing as x squared minus x minus 2. 0 equals x minus 2 and 0 equals x plus 1 is how we set it. We now set these two things equal to 0, so we've got 0 equals x minus 2, 0 equals x plus 1, and we get x equals 2 and x equals negative 1. We found all the solutions for this polynomial. Why does this work, though? We haven't really thought about why it works. And we don't want to just take things down from on high and automatically go, well, my teacher told me, so that must be the right thing. You want to understand why it's the right thing. Teachers can be wrong sometimes, so you want to be able to verify this stuff and go, yes, that makes sense. Or at least have them explaining and saying, well, we don't understand quite enough yet, but later on you'll be able to see the proof for this. You really want to be able to believe these things beyond just having someone tell you by word of mouth. So to figure out why this has to be the case, we'll consider 0 equals a times b. The equation is only true if a or b, or both of them, is equal to 0. If neither a nor b is equal to 0, then the equation cannot be true, right? If a equals 2 and b equals 5, then we get 10, which is not equal to 0, right? So as long as a or b is 0, it will be true, right? Because it will blow out the other one. But if both of them are not 0, then it fails and it's not going to be 0. It's the exact same thing happening with x squared minus x minus 2. We've got 0 equals x squared minus x minus 2, which we then factor into x minus 2 and x plus 1, right? So let's use two different colors so we can see where this matches up. We're pairing this to the same idea of the a times b equals 0. It's x minus 2 times x plus 1 equals 0. The only way this equation can be true is if x minus 2 equals 0 or x plus 1 equals 0. Just as we showed up here, it has to be the case that a or b equals 0 for that to be true. So it must be the case that either x minus 2 or x plus 1 equals 0 if this is going to be true. So our solutions are when either of the two possibilities is true, right? If the possibility is true, if one of them is true, then the whole thing comes out. So either case being true makes it acceptable. So that gets us 2, keeping with our color coding, 2 and negative 1 as the two possibilities. So by breaking x squared minus x minus 2 into its factors, we can find its roots. So this is how we find polynomial roots in general. First thing we do is we set the whole thing as 0 equals polynomial. We have to have some polynomial, and then it's 0 equals that polynomial. The next thing we do is we factor it into the smallest possible factors. We break it down into multiplicative factors, and then finally, we set each factor equal to 0, and we solve for each of them. So in step number 2, we're going to get things like 0 equals x plus a, x plus b, x plus c, x plus d, and so on and so on and so on. And then in step 3, we set each factor to 0. So we get things like x plus a equals 0, at which point we can solve and say, oh, x is equal to negative a. That's one of our possible solutions. And from there, you can work out all the roots of the polynomial. Caution, this is very important. Notice that it is extremely, extremely important to begin by setting the equation as 0 equals polynomial. I've seen lots of mistakes where people forgot to set it as 0 equals polynomial. If it isn't, if it was something like 5 equals x minus 2 times x plus 1, we can't solve for the solutions from those factors. Those factors are now meaningless. They aren't going to help us. We need the special property that 0 turns everything it multiplies into 0. Without that special property, this method just won't work. Consider if we had something like 5 equals a times b, right? There's no way that we can just figure out what the answers are here. It's not just simply a's got to be 0 or b's got to be 0, because a could be 5 and b could be 1, or b could be 5 and a could be 1, or a could be 25 and b could be 1/5, or a could be 100 and b could be 1 over 20. You know, we've got lots of different possibilities, a whole spectrum of things. There's way too many possible solutions. We need that special property of 0 equals a times b to be able to really go, that thing's 0 or that thing's 0. That's what we know for sure. That's how we get useful information out of it. So that's why it has to be 0 equals polynomial. If you don't set it up as that before you try to factor it, before you try to do the other steps, you're just not going to be able to get the answer, because we need that special property that 0 has when it multiplies other things. 0 multiplying something automatically turns it to 0. If we don't have that special property, things just won't work. Factoring is not necessarily easy. Say we've got something like x to the 5th plus 6.5x to the 4th minus 17.5x cubed minus 41x squared plus 24x, and we want to know its zeros. Well, if we knew its factors, we'd be able to break it into x plus 8, x plus 2 times x minus 0.5 times x minus 3, and it'd be really easy to figure out what the polynomial's roots are, right? At this point, we go, well, great. X plus 8 becomes x equals negative 8. X plus 2 becomes x equals negative 2. X plus 0 becomes x equals 0. X minus 0.5 becomes x equals positive 0.5, and x minus 3 becomes x equals positive 3. Great, found it really easy to find its roots. But how the heck do you factor a monster like that, right? There's the rub. Factoring can be quite difficult. Luckily, by this point, you've been certainly practicing how to factor for years in your algebra classes, right? By now, you've done lots of factoring. You're used to this. You've played with polynomials a bunch in previous math classes. And all that work has a use, and it's here, finding roots. We can break things down into their factors and find roots. But there's no simple procedure for factoring polynomials. Once again, right? Remember, if you were confronted by something like this, you'd probably have a really difficult time figuring out what its factors were, figuring out how you can break that down into factors. There's no simple procedure for factoring polynomials. High-degree polynomials can just be very difficult to factor. Happily, we're not going to really see such polynomials. Most courses on this sort of stuff don't wind up giving you very difficult things to factor at this stage, so we won't really have to worry about factoring really difficult polynomials. So we'll be able to stick to the smaller things. So let's have a quick review of how do you factor small things like quadratics. We're going to see a bunch of quadratics. They're very important. They pop up all the time in science. So let's look at a brief review of how to factor a quadratic polynomial. Remember, quadratic is a degree 2, and a trinomial just means 3 terms. So if we've got a quadratic trinomial in its normal form, then we've got ax squared plus bx plus c. If we want to factor that, we will turn it into a pair of linear binomials, right? Degree 1 and 2 terms, linear and binomial. So we'd want to break this into blank x plus blank times blank x plus blank. Great. To be equivalent to the above, the coefficients of x must give a product of a, right? So a has to come out with the red dot here times the red dot here. And the constants have to give a product of c. So the blue dot here times the blue dot here has to come out to be c. Also, b has to add up from the products of the outer blanks and the inner blanks. So it's got to be that the red dot times the red dot here times the blue dot here plus the blue dot here times the red dot here comes up to be this b here. So it's mixed out of the two of them. Don't worry if that's a little bit confusing right now. You'll be able to see it as we work through examples. So the b has to add up from the products of the outer blanks and the inner blanks. The a has to come from the first blanks, and the c has to come from the last blanks. Don't worry about memorizing this, though, just a sense of what's going on in practice. Let's look at an example. If we want to factor 2x squared minus 5x minus 12. So we know right off the bat we want to break it into the form blank x plus blank times blank x plus blank. First thing we notice is we've got this 2 at the front, and 2 only factors into 2 times 1. We can't break it up into anything else really easily, so 2 times 1, let's put it down as 2x times x. We've got to put the 2 somewhere, so it's either going to be 2x plus blank times 1x plus blank, or it's going to be the 2 over here and the 1 here. Doesn't really matter what order we put it in, so we'll put the 2 at the front. So we've got 2x plus blank times x plus blank. Now what's going to go into those other blanks? Now we need to factor the negative 12, so let's factor 12 first. We notice 12 can break into 1 times 12, 2 times 6, or 3 times 4. And one of the factors has to be a negative, because we've got a negative in front of the 12. So we have to be able to multiply to make a negative 12. So there's going to have to be a negative on either the 1 or the 12, right? One of those two will have to have a negative on it. We don't know which one, but it's going to be one of them. Or it's going to be negative 2 or negative 6. And then finally, for the last pair, it'd be negative 3 or negative 4. We're not going to use all of these at once. We'll have to figure out which one's right. But one of them will have to be negative because of this negative sign up here. We start working through this, and we know that there's this 2x here at the front. We've got this 2x at the front, so it's going to multiply this one, and it's going to effectively double whatever we put here. So the difference between one of the numbers doubled and its sibling, the one here times this one, so whatever's here times this 1 in front of it, must be negative 5, because we get negative 5x. We notice that 3 minus 2 times 4, 2 times 4 is 8, 3 is 3. So the difference between those is 5. So we can set it up as 3 minus 2 times 4 equals negative 5. And we get 2x plus 3 times x minus 4. And we've factored factored it out. We've been able to work it out. Now, there's various ways, various tricks have been taught, but the important thing, the various tricks have probably been taught to you in previous classes, but the important thing is just set up and have an expectation of what form you're trying to shoot for, and then plug things in and go, yeah, that would work, that would get me what I'm looking for, or no, if I plug that in, that won't work, that won't get me what I'm looking for. As long as you work through that sort of thing, you'll be able to find the answer eventually. It's always a good idea, though, to check your work. So you will find the answer, but it's really easy to make mistakes. So even on the easiest of problems, like the one we were just working on, there's lots of chances to make mistakes. Trust me, I make mistakes. Everybody makes mistakes. The important thing is to catch your mistakes before they wind up screwing you up. So it means that you should always try expanding the polynomial after you've factored it to make sure you factored correctly. And it's okay to do this in your head. Once you get comfortable with doing this sort of thing, and by now, honestly, you probably have had enough experience with this that you can just do this in your head reasonably quickly, it's okay to do it in your head. The important part is you want to have some step where you're checking back on what you're doing. So either do it on the paper if it's a long one, or do it in your head if it's something that's short enough that's easy enough for you to check. But you want to make sure you're checking your work. So for example, if we have 2x squared minus 5x minus 12, we figured out that that breaks into 2x plus 3 and x minus 4. But we want to check and make sure that it's right. So we check and make sure 2x plus 3 times x minus 4. So we get 2x squared, and then 2x times negative 4, 3 times x. So we get minus 8x plus 3x. 3 times negative 4, we get negative 12. We combine our like terms of minus 8x plus 3x, and we get 2x squared minus 5x minus 12. Sure enough, it checks out. We have what we started with, so we know that our factoring was correct. We did a good job. Factoring higher degree polynomials. In general, factoring polynomials of any degree is going to be similar to what we just did on these previous few slides. The only difference is it will become more complex as they become longer as we get to higher and higher degrees. So for example, if we had something like a cubic, if we had ax cubed plus bx squared plus cx plus d, we'd probably want to set it up as blank x plus blank times blank x squared plus blank x plus blank, right? If we're going to be able to break it up and factor it, it's going to have to factor into these two things, blank x plus blank times blank x squared plus blank x plus blank. Notice also this is a degree 1, and this is a degree 2. And when you multiply these two together, you'll get back to a degree 3 over here. Adding up the degrees on the right side has to be what we had on the left side. We could also work on a quartic, a degree 4, and we might try one of these two templates. If we have ax to the fourth plus bx cubed plus cx squared plus dx plus e, we might break it into blank x plus blank times blank x cubed plus blank x squared plus blank x plus blank, or we might break it into blank x squared plus blank x plus blank times blank x squared plus blank x plus blank. And so on and so forth, right? Clearly, this is going to become more difficult as we get to higher and higher degrees. The higher the degree of a polynomial, the more complicated our template's going to have to be for where we're going to fit things in, the more choices we are going to have, the more difficult it's going to be to do this. Luckily, we're only occasionally going to need factor cubics, things of this where it's degree 3, and we're very, very seldom going to see anything of higher degree, so don't worry too much about having really difficult ones, but just be aware that factoring really large, high-degree polynomials can actually be pretty difficult to do. Roots imply factors. We've got this useful trick up our sleeve if we want to break up these higher polynomials. If we know one of a polynomial's roots, we automatically know one of its factors. Remember, one use of finding the factors of a polynomial is to find its roots, right? If you find a factor of the form x minus a, then you set that equal to 0, and you know that that's going to be x equals a. It turns out that the exact opposite is true. If we know a polynomial has a root at x equals a, then it also means we've got a factor of x minus a. So if we've got a root x equals a, then that turns into a factor x minus a, right? Just because of this equation here, where we're setting that factor equal to 0, which gives us the root. We won't prove this. It requires a little bit of difficult mathematics and some stuff that we actually haven't covered in this course yet, but we can see it as a theorem. Let p of x be a polynomial of degree n. If p of x is a polynomial of degree n, then if there's some number a such that p of a equals 0, that is to say a is a root of our polynomial p, if we plug a in, we get 0, then there's some way to break it up so it's p of x is equal to x minus a, our factor x minus a that we know from our root at x equals a, times q of x, where q is some other polynomial of degree n minus 1, because this here is degree 1. So when we multiply it by a degree n minus 1, we'll be back up to our degree n polynomial that we originally had. If we manage to find one or more roots, sometimes the problem will give them to us, other times we'll get lucky and we might just guess one. This theorem means we automatically know that many factors of the polynomial. For example, say we know that p of x equals x cubed minus 2x squared minus 13x minus 10, and we're told that p of 5 equals 0. We know that 5 is a root. Then we automatically know at x equals 5, we've got a 0, so x minus 5 is our root. We plug that in, we know it's going to be x minus 5 times blank x squared plus blank x plus blank. Now, we don't know what is in these blanks yet. We still don't know what's going to be in there. But we are one step closer to figuring out what those factors are, for being able to figure out what has to go in those blanks. Later on in another lesson, we'll use this fact to great advantage, this fact that knowing a root automatically means you know a factor, when we learn about the intermediate value theorem and to help us find roots, and the polynomial division using those roots to break down large polynomials into smaller, more manageable factors. Not all polynomials can be factored, though. Even with all this talk of factoring polynomials, there are some that cannot be factors. Not because it's difficult or really hard to do, but because it's just flat out impossible. Consider this polynomial. F of x equals x squared plus 1. If we try to find its roots, then we've got 0 equals x squared plus 1. So we've got x squared equals negative 1. But there's no number that exists that can be squared to become a negative number. No number can be squared to become a negative number. Why? Consider, if we've got negative 2 squared, that becomes positive 4. If we square any negative number, it becomes a positive number. If we square any positive number, it stays positive. If we square 0, it stays 0. So there's no number that we've got that we can square and get a negative number out of it. Thus, the polynomial has no roots, and since it has no roots from that theorem we just saw, it can't have any factors. So it has no roots, therefore it cannot be reduced into smaller factors, and something that cannot be reduced we call irreducible. It is not reducible. Now, I'll be honest, what I just told you isn't really the whole story. So more accurately, we can't factor all polynomials yet. The previous slide that we just saw is perfectly true, but only if you're working with just the real numbers, which has the symbol are like that. Now, that's what we're normally working with, so it's kind of reasonable to say this. But it turns out there's a hidden type of number that we haven't previously explored. You might have seen this in previous math classes even. We'll learn about the complex numbers later on. Complex numbers can give us a way to factor these supposedly irreducible polynomials. So they're irreducible for real numbers, but they're not irreducible for complex numbers. Now, we'll learn about them in the lesson that's named after these numbers, our lesson on complex numbers. But for now, we're just working with real numbers, and in general, we'll just be working with real numbers in this course. Real numbers are really useful. You can do a lot of stuff with them, so it's enough for us to be working with real numbers generally. So that means, for us, right now at least, some polynomials are simply irreducible, and we can't always find roots for everything in a polynomial because we can't break it down because there are things that just don't have roots based on how real numbers work. Now, we'll talk about complex numbers later on, but I just wanted to point this out that I'm not telling you the whole story right now because we don't want to get confused with complex numbers. But for our purposes right now, real numbers, there are some things that are simply irreducible. There is a limit to how many roots or factors a polynomial can have. Now, roots, factors, they're basically two sides of the same coin, right? Since x equals a as a root is the same thing as knowing x minus a as a factor. So they're just two sides of the same coin, so we'll consider them as roots factors, a polynomial. A polynomial of degree n can have at most n roots factors. So we can have a maximum of n of these guys. Why is this the case? Well, consider this. Every factor comes in the form x plus blank, right? Or even larger if the factor is irreducible, right? It might be blank x squared plus blank x plus blank. But the very smallest, it's got to be x plus blank. If we break a polynomial into its factors, we're going to get x plus blank times x plus blank times so on and so on up until x plus blank. Now, if we had more than n factors, then that would mean that we've got x plus blank multiplying by itself more than n times. So if we have x multiplying more than n times, then it's got to have a degree of larger than n, right? Its exponent is going to have to be greater than that, right? If we wanted to max out at x squared, but we had blank x plus blank times x plus blank times x plus blank, well, that's going to become x cubed plus stuff after it, which is not going to be x squared, not going to be degree 2. So if we've got a degree n polynomial, the most factors we can possibly have is n factors, n roots, because otherwise we'd have too many factors and we would blow out the degree of the polynomial. Thus, the most roots factors a polynomial can have is equal to its degree. We also can get information about the possible shape of a polynomial's graph from its degree. A polynomial of degree n can have at most n minus 1 peaks and valleys. Formally speaking, that is the relative maximums and minimums. So for example, if we've got x to the fourth, then that means we've got n equals 4, our degree. So n minus 1 equals 3. So 3, we look over here and we've got one valley here, one peak here, one valley here. This is also a relative minimum. A relative minimum, that's what we mean by valley, and a relative maximum. That's what we mean by peak. So n minus 1 tells us the most bottoms and tops we can have before they either go off to positive infinity or go off to negative infinity. Now, we can't prove this here because it requires calculus, but it is connected to the maximum number of roots in a polynomial. And if you go on to take calculus, which I heartily recommend, you will very clearly, very quickly see it. It becomes very clear in calculus. It's one of the important points of what you do in calculus. So you'll go, oh, that makes a lot of sense because the possible peaks and valleys are connected to a polynomial that has a degree that is 1 less, and that's why it's connected. Don't worry about it too much right now, but it's very interesting and very obvious if you go on to take calculus. Notice that in both of the previous properties, it was described as at most, right? Just because a polynomial has degree n does not mean it will have n distinct roots or n minus 1 peaks and valleys. We aren't necessarily going to have that many. It's just we can have up to that many. Consider f of x equals x to the 5th plus 1. This graph's like this. But from this graph, we can see clearly we've only got one root, and we've got no peaks or valleys. The degree gives an upper limit on how many there can be, but it doesn't tell us how many there will be. It just says there's maximum is this, but you could definitely have fewer. All right, we're ready for some examples. First one, we want to find the zeros of f of x equals 3x squared minus 23x plus 14. So textbook example, we just literally a textbook example since this is effectively a textbook. So you plug in 0 because we're looking for when is f of x equal to 0. 0 equals 3x squared minus 23x plus 14. So we know we're going to be looking for 0 equals something where it's going to be blank x plus blank times blank x plus blank, right? So what are we going to slot in there? Well, we notice, hey, here's 3. The only way we can break up 3 is 3 times 1. There's no other choices, so we've either got to have 3 go for the first x or 3 go to the second x. So let's set it as 0 equals quantity 3x plus blank, and we'll have 1x, so just x plus blank. Great. Now at this point, we also say, hey, we've got 14 over here. How can 14 break up? Well, we can have 1 times 14, or we can have 2 times 7. Those are the only choices. So we're going to have to plug in either 1 times 14 or 2 times 7. But now we also have to take this minus 23 into consideration. If we've got minus 23, then we're going to have at least one negative over here. And since it comes out as a positive, it's going to have to be that they're both negatives. So one of them's negative, so they'll both be negatives. So it would be negative 1 times negative 14 or negative 2 times negative 7. So negative 1 times negative 14, we'll notice that either way that we put that in, that won't work out. But we can plug in negative 2 times negative 7, and we can amp up this negative 7. So plus negative 7 here. Put in the negative 2 here, and we get 0 equals 3x minus 2 times x minus 7. We've managed to factor it. Let's really quickly check what we have here. Does this work out? Check. 3x minus 2 times x minus 7. So we'd get 3x squared minus 21x minus 2x plus 14. So 3x squared minus 23x plus 14 checks out. Sure enough, it's good. So at this point, we break this down into two different possibilities. Either 3x minus 2 is equal to 0, or x minus 7 is equal to 0. So 3x minus 2 equals 0, or x minus 7 equals 0 are the two different worlds where this will be true, where we will have found a root, where the whole expression will be equal to 0. So 3x minus 2 equals 0. We get 3x equals 2. X equals 2/3. Over here, x minus 7 equals 0. We have x equals 7. So our answers are x equals 2/3 and x equals 7. Those are the roots to this polynomial. Great. If f of 2 equals 0, factor f of x equals x cubed minus 7x plus 6. So remember, if we know that at x equals 2, we've got a 0, so at x equals 2, there is a root, then that means there is a factor in that polynomial of x minus 2. How do we figure that out? Well, we notice x equals 2, then it's x minus 2 equals 0, so that implies that it's got to be a factor of x minus 2 in there. We can use that piece of information, and we know that f of x is going to have to break down with an x minus 2 in there. So let's set it up like normal. 0 equals x cubed minus 7x plus 6, but what we just figured out here, we know that there's a factor of x minus 2. So we can also write this as 0 equals quantity x minus 2 times blank x squared plus blank x plus blank. So what are going to go into those blanks? Well, at this point, we just use a little bit of logic and ingenuity, and we can figure this out. Well, we know that what is in front of this x cubed? Well, it's effectively a 1. So if there's a 1 in front, we've got x times x squared. Whatever goes into this blank is going to determine what coefficient is in front of it. So since we want a 1, it's got to be that there's a 1 here as well. What about in the very end? Well, the only thing that's going to create the ending coefficient, sorry, not the coefficient, the ending constant is going to be the other constants, right? So the constants that we have here are negative 2 and whatever goes into that blank. So it must be that negative 2 times blank here becomes 6. Negative 2 times negative 3 becomes 6. So we've got a negative 3 here. And finally, what's going to go into this blank here? So we think about this one, and we know that we want to have 0 x squared come out of this, right? There's no x squareds up here, so we've got plus 0x squared. So whatever comes in here must come out, whatever we put into this blank must somehow get us a 0x squared to show up. So x times x squared, that's x cubed, so we're not going to worry about that. But x times blank x is going to be x squared. So let's do a little sidebar for this. So x times blank x will become blank x squared, and minus 2 times minus 2 times, we already filled in that blank, 1x squared is going to be minus 2x squared. Now we want 0x squared out of it, so it must be when we add these two things together, it comes out to be 0x squared. So what does this have to be? It's got to be positive 2x squared. So we know that positive 2x squared minus 2x squared comes out to be 0x squared, so it must be that this is a positive 2x. So we write this whole thing out. 0 equals quantity x minus 2 times quantity x squared plus 2x minus 3. And we've been able to figure out that that works. We check this out, do a real quick check. So check x cubed plus 2x squared minus 3x minus 2x squared minus 4x minus 6. X cubed, that checks out. 2x squared minus 2x squared, those knock each other, that checks out. Minus 3x minus 4x, that becomes minus 7x, so that checks out. Minus 6, that checks out as well. Great, so we've got a correct thing. So 0 equals x minus 2 times x squared plus 2x minus 3 is correct. We've factored it properly. So at this point, the only thing that we have left to factor is the x squared plus 2x minus 3. So 0 equals x minus 2 times blank x plus blank times blank x plus blank. What goes in those first blanks? Well, we've just got a 1 in front of that, so it's 1 and 1. Don't have to worry about that much. What else is going to go in there? Well, negative 3 at the very end. We've got plus 2x, so it must be that the negative amount is smaller than the positive amount, so it's going to be plus negative 1 and plus 3. Negative 1 times 3 gets us negative 3, and everything else checks out, right? X times x, x squared, plus 3x minus x, that gets us plus 2x, and minus 1 times 3, that gets us negative 3. So that checks out. Did another check in our heads real quickly. So finally, we've got 0 equals quantity x minus 2 times quantity x minus 1 times quantity x plus 3. We break this up into 3 different worlds. Set each world equal to 0. X minus 2 equals 0. X minus 1 equals 0. X plus 3 equals 0. So we've got x equals 2, x equals 1, x equals negative 3. Those are all the roots for this polynomial. All right. Next example. Give a polynomial with roots at the indicated locations and the given degree. Now remember, a root can become a factor. So if we know that we've got a root at negative 3, then that becomes a factor of, if it was x equals negative 3, then it would become x plus 3. If we had x equals 8, then that would become x minus 47. If we had, whoops, sorry, I accidentally read the wrong one, read forward one. Sorry about that, x minus 8. And then finally, if we had x equals 47, we'd have x minus 47 as our factor. So those 3 things together, we've got x plus 3 times x minus 8 times x minus 47. And that right there is a polynomial. We know it has degree 3 because we've got x times x times x. That's going to be the largest possible exponent we can get on our variable. That'll come out to be x cubed, so we've got a degree of 3. And we know it has roots in all the appropriate places. And we're done. That's it. So we could expand this and we could simplify if we wanted. We weren't absolutely required to by the problem. And this is a correct answer. It is a polynomial. It's not in that general standard form that we're used to of blank x to the exponent, blank x to the exponent, blank x to the exponent. But it is still a polynomial, so it's a pretty good answer. We'll leave it like that. Next one, we've got negative 2 and positive 2. So we've got x plus 2 for the negative 2 and x minus 2 for that. Y, x equals negative 2, we move that over, we get x plus 2 equals 0. X equals positive 2, we move that over, we get x minus 2 equals 0. So we get x plus 2 times x minus 2. But if we multiply those two together, we just have a degree of 2, and we want a degree of 4. So we need to somehow get the degree up on this thing, but have the same roots, not have to accidentally introduce any more roots. So if we introduced multiplying just by x twice, we'd have introduced a root at x equals 0. So we can't just do that. But we do realize, oh hey, if we just increase this to squared on both of them, they'll still have the same roots. It's just duplicate roots showing up. So x plus 2 squared times x minus 2 squared. We've hit that degree of 4 because each one of these will now have a degree of 2. Alternately, we could have done this as x plus 2 to the 1, x minus 2 cubed, or x plus 2 cubed, x minus 2 to the 1. Any one of these would have degree 4 and have our roots at the appropriate place. Great. Final example, what is the maximum possible number of roots and peaks/valleys for each of the following polynomials? So for our first one, f of x, we notice, hey, this has got a degree of 3, so n equals 3 means maximum number of roots it can have is 3, and max peaks/valleys is 1 less n minus 1, so n minus 1, 3 minus 1 is 2. So maximum number of roots is 3, maximum peaks/valleys is 2. We don't necessarily know it will have that many. All we know is that's the maximum it could possibly have. Next one, we notice the degree for this one is 47. So if n equals 47, then the maximum roots are going to be equal to that degree. Maximum peaks/valleys is going to be 1 less than that degree. So we will get 46, 1 less than that. Final one. For this one, we go, oh, 10 cubed, so 3. No, we have to remember, this is not a variable. This here is a variable, so it's x to the 1, so its degree is just 1. So for that one, so degree 1, we'll change over to the color green. So n equals 1 means maximum roots is just 1, and the maximum peaks/valleys is going to be 1 less than 1, so 1 minus 1 equals 0. Now, why is that the case? Well, think about it. 10 cubed x minus 5, well, 10 cubed, that's just some constant, happens to be 1,000, but not really the point. So 1,000 x minus 5, well, that's just going to be a very steep line, right? X minus 5, so it'll intersect here, but does it ever go up and down? Does it ever undulate in weird ways? No, it never does anything. We've just got a nice straight line since it's a linear thing, linear like a line. So since it's a linear expression, never undulates, never has any peaks, valleys, so it never has any relative maximums, no relative minimums, and that's why we've got 0 there. Makes sense. All right, hope everything there made sense. Hope you got a really good understanding of roots, because roots will come up in all sorts of places. Really important to understand. Really important to understand this general idea, because you'll see it in other things being changed around. But if you understand this general idea, you'll be able to understand what's going on in later things in different courses. All right, we'll see you at educator.com later. Bye.